Okay, so we had a logical break. We had completed the combinational circuit design. We talked about all the MSIE circuit elements in combinational circuits. We talked about iterative networks. We talked about regular structures. Okay, and now we are on set to start the sequential circuits. But I thought let's give a break to circuit design and come back to the last chapter in the syllabus, which is VHDL. So I thought I'll give a quick overview on VHDL, because VHDL is not something which can be taught just in class. It comes by the practice. So what I expect is I'll cover it a bit in the lectures, and we will start using it in the laboratory classes. And I think it will become much more meaningful when you do a digital system design using a hardware description language. You can simulate, you can see the performance on your laptops or desktops, whatever you have at your homes. So, and this we will tell you a freeware which is available for a simulation of VHDL if not known already. So that will be provided to you. So you can download and you can start doing it. And I think it will become much more meaningful as compared to what we are doing right now in a digital lab. So I am only giving you an introduction, and not everything I have created. I have taken some slides from Professor Nitin Yogi of Auburn University, and I have also taken some slides from Professor Raj Singh, who is in Siri Pilani. Obvious reason, I had been the team member there and I have worked together. So, a brief introduction, hardware description language. In short, it is known as HDL. So hardware description language is a language to describe hardware. Okay, now since you are in the domain hardware software co-design, you talk about electronics, you talk about programming, I think this is the most meaningful thing for you, that how do you define your hardware in a language and still get everything done by electronics. So that is the way what HDL platform provides you. There are two popular languages for hardware description. One is called VHDL and second is called Verilog. Okay, VHDL stands for, you can see over here, V in VHDL is for a project. This was a project in US for military services, very high speed integrated circuits. I'll give you some history in a minute. So this V comes from that project, and HDL is for hardware description language. This was developed by Department of Defense in 1983 time frame, and this was the IEEE standard for VHDL. 1076 is the standard, and then there are various versions. So you will have 1076 1987, the first version, which was IEEE standard. Second was 1993, and then it was 2003, if I remember correctly. This is similar, something similar to ADA language. And the second is the Verilog. Verilog is standard 1364. The constructs are slightly different. Verilog is more similar to C language. Yes, please. If you know C, Verilog coding is very easy. Okay, but as a part of this course, we have opted for VHDL because VHDL is a superset, and VHDL tells you the strength of hardware description language, and there are many things which can be done in VHDL but cannot be done with Verilog. Although the Verilog is the most popular language in industry. But I know if you know VHDL, Verilog can be adapted just in 2 days. If you know Verilog and C, coding in Verilog is not difficult at any level. Okay, so eventually we will give you an option to do a project in Verilog or VHDL, anything. But right now we will start with VHDL in the lab. A little bit of history. It is 1981 when department. Here, if you have to speak, you can mute now. You are talking to, I don't know whom. This Department of Defense, USA, launched a project which is very high speed integrated circuits, which is the VHSIC project, a very popular project. And that was the first time when they were designing integrated circuits for defense applications. So in 1983, there was a request from US government, which was called request for proposal, and it is a very standard term which is being coined there, to develop a language which can kind of describe hardware. So they first coined the word HDL, and they said, develop a language which can kind of code the hardware in software. And therefore, this language was developed as a part of that project. Kindly give me a second break. I'm coming back in a second. Sorry, there was a lot of noise which was coming to my office, so I had to go. There was a kind of lot of people make their stake, and this was a team which was Intermatics, IBM, and Texas Instruments, which finally won the competition, and that language eventually was converted to VHDL. In 1985, the VHDL version 7.2 was made available to the users. And in 1986, initial suite of support software was released. That means the first software which could simulate VHDL, and the standard VHDL was made available. 1987, the IEEE adopted it as a standard and released it, which was called VHDL 87, because it was done in 87, that is why. And then this code was revised in 1993. Okay, this was the time frame, 1988. I also entered my professional life, and I started doing VLSI design chips. And in 89, we started using VHDL. We heard VHDL is something very great which has come up. And we were given one project where we were to design a microprocessor using VHDL. So they had not asked us to use VHDL. The challenge given to us was to design a microprocessor which is compatible or pin compatible to microprocessor which is 68010 from Motorola. So pin-to-pin compatibility was expected, and timings were to be matched. The instruction cycle and all those details had to be matched. But it was to run on a higher frequency. And they had said at least make 4 times the frequency of that processor. That processor was running only at 10 megahertz at that time. So we were given a target of 40 megahertz. So we were thinking about how to design a microprocessor. We had nothing but for the user manual, which had all the instructions, their machine cycles, that information we had. So we decided to use a hardware description language. And at that time, our team manager, as you call, or the group leader, Dr. Chandrasekhar, taught us VHDL like I am trying to teach you in class, but we did it for a longer duration, and we were given a lot of projects to do before we could start microprocessor design. So it was in 1993 that we also came out with our VHDL version of the design. The processor we had done completed in VHDL, which was simulated, synthesized. Everything was done using VHDL. So a big electronic system design or circuit design, if you want to do, and today, if it is big, it's not that everything you can do using gates. You need a support of a software to design your hardware. So VHDL sets that platform. Okay, and these are further standards which have come up. I think we are not much interested into each and every standard. We can look up on the literature and get back to it. So it becomes very meaningful to study from digital system design point of view. Now, I also repeat that this VHDL which I am teaching, the original VHDL was only for digital system and circuit design. Eventually, analog designs can also be done with VHDL, but that VHDL is known as AVHDL. Okay, so analog VHDL. So there it has some additional capability to model analog elements. We are not talking about them, and we are not interested at this point in time because the domain of the course is digital systems. So what are the applications of HDL? You can model a hardware, you can document a hardware in that language. The language is such, it also helps you to document. So you don't have to create an additional documentation for it. There are various levels of abstraction. The way you design your hardware, you can design its only a behavior where you state how outputs behave with respect to inputs. You can also define its structure, for example, which gates to connect where and what is the net list to realize a particular functionality. You can also have a data flow model where how signals propagate with time. Okay, and you can even have a mixture of any of these three, that you can combine any two or any three and you can build. Because at times when you are designing a digital system, you are at the top abstraction level, that you know behavior of most components, but you know structure of some, so you can add some structures. If you think for this particular block, I know the data flow, you can add data flow. So you can combine anything. Then you can, the first thing we said is documentation, modeling, two things. And then you can simulate it to verify whether it is behaving the way you want it. So you can check the behavior, input versus output, etc. And the third or the last important thing is you can synthesize the circuit. So when you say the behavior, and if your code is synthesizable, you can convert your VHDL code from that high level abstraction level to low abstraction level, which is gated netlist, as simple as gated netlist. Okay, so maybe for example, you model a adder. You all understand adder. So you were making a 16-bit adder. So you can model it. You can even write statements to document what you are doing. Then you can simulate that adder to check whether it is doing all additions correctly. Now it depends. Will you like to check for all the combinations? Because if you have 16-bit adder, you have two operands, and each operand can have 2 to the power 16 variants. So you need to combine each and every variant of the two operands to test it 100%, which is typically not done. You pick up only the select cases which are critical or significant cases, and if they work, you say my design is working. And most probably 99.99% the design will be working. After that, now you had said A plus B is equal to C, for example. So that was your modeling, and A was a 16-bit vector, B was 16-bit vector, and you were getting a C result, which was 16-bit vector. But when you synthesize at the gate level, it's not just saying plus sign or something. You have to have a gated network for each bit. So synthesis means conversion of your that language to a hardware. So it becomes very meaningful. You don't have to do a gated network design. You write in a software and you convert it to the hardware. So I think it should interest you a lot. Now, how do you model a hardware in VHDL? A hardware model in VHDL is described in two parts. Okay, one is entity declaration part, and then there is a associated architecture body. Now, these are the two important things, or two important units which are there. I'll come to what are units. So entity would describe the IO interface, like what are my inputs, what are my outputs. If I have any pin which is both input and output, all those options are there. We will talk about their types, what all I can define. And then inside, whatever is the inside of that chip is the behavior, how output should behave as a function of input. Now that can be defined in various ways. So this one entity can have various architectural bodies which define the behavior. Okay, and this entity declaration, see, the entity declaration gives a name to the model being developed and also declares its external interface signal, also called ports. So we will talk about what is signal, what is port, what are their modes. I said input, output, input, out, in, out, and there is a buffer and their types, everything, all these things we will talk about. But you should have an overview, like if you are defining a AND gate, simplest entity. So this unit will only, entity will define there are two input ports, okay, and there is one output port. That is all you are defining. The inputs are Boolean or bit. We will choose. We will see what is the difference between Boolean and bit. And your output is also of the same type, Boolean or bit. Again, just one. And then we come to the architecture body. Now, the architecture body defines the internal details of the model. It can define even internal signals, one or more concurrent statements that together model the hardware. What is a concurrent statement? Now, you have done C language. How your program executes is all sequential. Whatever statements you write, they are executed one after the other, in which order they appear. Now, hardware is not something which works sequentially. If you have, for example, a 1-bit full adder, you will recall you have a XOR gate and followed by another XOR gate. And then you have, maybe I'll draw, I'll use this and I will do a notation and draw somewhere. This is your A, B, and this is carry in, and this is your sum. And similarly, you have A, B, and there is one more I should have done, but I have less space over here, and then OR gate. Now see, all these gates are active all the time. They are working. Whatever input is their corresponding output, they will be giving all the time. It's not that first this gate will work, then this gate will work, or this gate will work. Nothing doing. Everything is active all the time. The only difference is whenever the inputs change to a particular gate, the corresponding output will change. If any changes there, this will change. If any changes here, this will change. Any change over here, this will change. And wherever there are changes, those corresponding gate outputs will change. Okay, so everything is kind of being executed concurrently. So that is the difference between a C language and a hardware description language. So I need concurrent statements in hardware description language which can define my structure. We will talk more about concurrent and sequential statements later. We also need sequential statements when we are describing the behavior. For example, here I can describe, if I'm describing a behavior, maybe I compute the behavior of this, I use the output of this and compute the behavior of this. So if I'm writing that kind of a code, I will need sequential statements also. But many times I need only data flow equation model is all concurrent. Okay, so we will talk about those details. First, let me define. Multiple architectures are allowed to be defined for one entity. I said it earlier too. Now this represents the designer's description, design's description at various levels of abstraction, or multiple implementations of the same design specs. Although only one of them can be selected at a given point in time when you are simulating it. You can define multiple behaviors. Okay, for example, even adder. I may design a adder using XOR and OR gates. I can design the adder with only NAND gates. So these are two different circuits. Behavior input output is the same interface is there, but the way I define the internal structure, that could be different. Okay, so but when I'm doing a simulation, I'll pick up entity and I can pick up one of the possible architectures. I can write many architectures, but simulation one at a time. I have already said that there are various ways of describing internal behavior, and one or more coding styles from the three styles which I mentioned. These are the three styles: behavior, structure, and data flow. So what are these styles? We will talk about later. Another thing, you please note that VHDL is case insensitive. Okay, so if you are writing a signal with small or capital, it is one and the same thing. It will be taken as the same signal. Now this is one example how I do a input output specification of a circuit. So let's say this is my circuit, which is having 3 inputs and 2 outputs. And what I have tried to do is something what we used to do, let me not name anything, but we will see. The inputs you can see A, B, C, okay? And you have outputs X, Y. This is what I want to. So this is the description of this circuit, the entity description of this circuit. This entity is the keyword. My circuit is the name of the circuit which I have given. So there is a way how you can write this name using alphanumeric characters and few more characters. And then this is again is keyword. Then I define the port. These are known as ports. So I write the port, and within the brackets, I define what all input and output ports are there. Now see A, B, and S followed by colon. This is syntax. In is keyword, which is the type of this port, and bit is the type of the data which it can take. So bit would mean it can take either bit 0 or bit 1. Okay. And same XY are output. So you can see that the mode has changed and the type of the data is the same. And then you say and my circuit. You can also write a and entity my circuit. So we need to kind of follow syntax as we do in C language, but you can code. I think this is the same. Now, this is what is some more elaboration. You can see this is the name of the circuit and which is user defined. And you can even use a file name as the circuit name. This is a kind of a recommendation so that you know what model you are talking about. So here we have used a circuit name, my circuit, and file name will be saved as my/circuit dot VHD. Dot VHD is the extension which is used for all the VHDL codes which you write. Now see here, these are port names or signal names. All ports are taken as signals. We will talk about what else you can have. There are variables which can be used and there are constants which can be used, but the input and output is always through signals. What are the differences? We will talk about. Then this is the mode, the direction of the port. So typically we use only 3 types of ports: in, out, and in, out. Buffer is very rarely used. We will talk about it somewhere if required. Otherwise, I'm not intending to cover buffer in this particular course. Then this is the data type. And you can have data types which are user defined. You can have data types which is inbuilt into VHDL. There are a lot of inbuilt kind of data types available, and you need to include a particular library, whatever you are using. Okay. And if you want to define your own user type, user defined type, and that has to be again declared in the library and included in the code. We will talk about libraries, packages, and everything, how to make them and how to use them. Now, kindly note this semicolon over here. The semicolon in after the last port is not written. It's only written after the bracket closure. These are separating, the earlier semicolons are separating the various ports. Okay. Now coming to, because the first thing what we need is the data types. So what are the built-in data types? There are scalar data types which are single valued signal types. So they are bit, Boolean, integer. So examples are, for example, we just talked about bit, which can take value 0 and 1. I can also use Boolean type. Then when I say Boolean, it means true and false. These are the 2 possible values. You can have integer. Integer can have variety of ranges. You can define your own range. Else there is a predefined range as well, which is available, which depends upon the size of the register or the system which you are using. If it is a 32-bit processor, so it will have something 2 to the power 31 on minus sign, minus 2 to the power 31 to 2 to the power minus 31 minus 1, which is 30. So it just 32 to 31, sorry. So this just is dependent upon where you are using the VHDL code, what do you want to do it, what kind of range you want to define, you can do it. Okay, then there is a aggregate collection of signal types. For example, bit vector. For example, if I have a 4-bit adder, so my A operand is 4-bit and B operand is 4-bit. So I need not define each and individual bits over there. I can define a bit vector. So A will become my bit vector. So for example, if it is 4-bit, I will write A colon in bit vector 0 to 3. Okay. I can also write 3 down to 0. It just depends upon me how I want to define it and use it. Okay. Now you can have signed kind of numbers. So see, this is array of bits representing signed binary numbers. So otherwise it's only unsigned magnitudes. And if you want it signed, then you have to define it a different type. Okay, so these are some of the examples. You can also construct data types arbitrary or using built-in data types. The example is, for example, I can build a type temperature. So temperature is my type, and I can say is high, medium, low. I have only three kind of temperatures, which is high, medium, and low. Okay. I can also define a type byte. Byte is nothing but an array of 8 bits. So I define it is an array 0 to 7 of bit. So I can have those kind of flexibilities. Now this type, which has these kind of values, is known as enumerate type. Okay. And this enumerate type is only available in VHDL. It is not available in Verilog. Now, next is the functional specification of my circuit. Now, let's say the behavior of my circuit, I have two outputs, X and Y. So the behavior of X is, let's say, when S is equal to 0, A goes to X. Yes, please. Yes, please. Any question? Shreyash Dubey. Okay. So the behavior is, let's say when S is equal to 0, A goes to X, but if S is equal to 1, B goes to X. A 2:1 multiplexer kind. Okay. So, and the behavior of Y is when X is equal to 0 and S is equal to 0, then Y takes the value 1, else Y takes the value 0. So these are two different kind of behaviors for the two outputs, but I can define any behavior, and how will I code it? So let's say if I define this in a behavioral code, okay, this is a behavioral code. The first code, we said three codes: behavioral, structural, and data flow. So let's say we are defining it as a behavioral code. If you write a behavioral code, then it is sequential in nature within the process statement. So this process statement is concurrent, and whatever I write within this will be executed sequentially. Okay, so within this process statement, all the things what I can write is sequential. So I can write any sequential statement, whether it is assignment statement, I can have if then else, I can have switch, and many more. And we will talk about what are those statements. Okay, so this is just, I'm taking one overview example. So this is another unit we are talking about is architecture, which defines the behavior. So again, this is architecture name, which is assigned by user. Now see, here you have to write, this is architecture of which entity? So this is the name of the entity is, and then you write begin, and then since behavioral model, so you have to write a process. P1 is the name of this process, which you can write by a name followed by a colon, and then this is process is keyword, and within bracket, this is called the sensitivity list. Okay, so when should this process get activated? Because concurrent statement only get activated when there is an event on a said signal. So whenever there is a event on A, B, or S, then this process will get activated. Now, what is an event? Event is change of a value on a particular value. So if they are bit type, if A changes from 0 to 1 or 1 to 0, it is called an event. Similarly for others. Now, if there is an event on anything, any of these three, what it will do is it will check S is equal to 0, then it will make X take the value of A, else it will assign value B to X, closed. Then it will come over here, it will again check the value of X, value of S, and assign the new values to Y. I end the process and go. So I have written both the statements, what is goes on Y and what goes on X. Okay, so this is one behavioral explanation or a description of my circuit. So see here, uh, here the problem is, now see, this is what I will try to write a code when I have defined my behavior. You remember the second input output Y, we said whenever X is equal to 0 and S is equal to 0, I want to do this. But see, X was defined as a output of the type mode was out. Okay, so out cannot be used as a input in the my design. So this will, when you try to simulate this, this will give you an error. Okay, and the value of X will not be read by my code or the simulator. So what do? I have solutions, we will talk about it. So you need to the solution is you have to have a internal signal, which you can call it xtemp. Okay, so now what you are doing is your process is also sensitive to xtemp. Okay, the three inputs and the temporary signal which we had defined. Now A and B, rather sending to X, what we were doing earlier, I'm only sending it to a temporary signal. Now I can use this temporary signal to define Y, and whatever is the value of xtemp, I can send on to the X as well. Now this will solve my problem and I will not have an error on my code. Now, though it was a very simple example, but it's important when to use a internal signal or an additional signal internally to make your code run. Okay, so some of the comments, signal can only be defined in this place before the begin keyword. So if you are making any additional internal signal declaration, it can only be done in this space. Thereafter, you cannot. General rule include all signals in the sensitivity list of the process, which either appear in relational comparison on the right hand side of the assignment operator inside the process construct. So you need to include all of them. Kindly try to do that. Oh, okay. I think I am running out of time, and I will take up the concurrent behavior description, which is data flow model, next time in the next class. Any questions so far? Yes, I can share the slides. Um, give me a couple of days. Let me finish off making my all the slides which I want to do it for next 2-3 classes, and then I will share with you. And I will give you, one question is what is IDE for it. So we will provide you. Let me sort out which one is suits better to you, which you can freely download and use at least for a month. Okay, then I'll make it available. Anything else? Okay, then we will stop over here, and we will continue in the next class. Thank you.